We're going to talk about rational exponents and radicals today. So first, let's talk about what a radical expression looks like. So you guys have seen some radical expressions. It's just been a while. So the parts of a radical expression here. So this part here, the part that kind of looks like that division symbol, but it's got like a little tail on it, that's called the radical sign. And we're going to talk more about that right now. All right. The number inside of the radical sign is called the radicand. Not the radicant. You're exactly right.
Ew, you heard that?
Yes. And finally, this number out front is called the index. Index. The index. Do I need to write that better? I apologize. I can make it better. There we go. So the index, you guys are used to seeing the index as a 2. So for example, if I have the square root of 9, right? It's understood that there's a 2 there. Does that make sense? And we're going to talk about different indexes here in just a moment. But first I want to talk about how to write an exponential expression as a radical expression. So my first example, I have a to the 1/nth power. I can rewrite this as the nth root of a. I had someone last period ask me, well, what happened to the 1? That's a to the 1 power. All right. A to the m over n power, that's going to be the nth root of a to the m. So what happens here is your denominator and your fraction of the exponent becomes your index. That's one way to rewrite a radical expression. All right. So we're going to use this to rewrite these radical expressions in simplified form. So to do that, what we have to do first is we have to find the prime factorization of your radicand. So to do that, I'm going to take 125. I'm going to zoom in a bit here so we can see better. There we go. So I'm going to take 125. What's the smallest prime number that will go into 125? Does 2 go into 125?
No,
Because there's a 5 at the end, right? Does 3 go into 125? Probably. How many times? 5 definitely goes into 125, right?
Like 25.
5 goes into 125 25 times. All right? Is 25 prime? No, so what goes into 25? 5, how many times? 5. And then 5 is prime, right?
Yeah.
So this is what I'm going to call the birthday cake method. And it's because, you'll see this kind of looks like a cake with layers. Hey, look at that. So these numbers on the outside are the icing. The icing are my factors of the radicand. Fondant factors, I love it. So let's rewrite this. So I've got the cubed root of 5 times 5 times 5. Well, if I have 5 times 5 times 5, I can rewrite that as 5 cubed. So if I rewrite this in exponential form, I'm going to have my base is my radicand, 5 cubed over what's my index? 3. And what is 3 divided by 3? 1. So that 5 to the 1 power is 5. Well, I'm showing you all of the steps. And B, you want me to skip some of the steps? Y'all want me to skip some steps and show you another way?
Yes.
Yeah?
Easier.
Okay. Well, I'll show you another way, and you're welcome to choose either way you prefer. Okay? I'm going to pause for just a second, though, because I see a lot of pencils still moving. All right, let's take a look at B. So I have the 4th root of 16, so I'm going to do the birthday cake method again. I'm going to find all my fondant, right? So I've got 16. What goes into 16? What's the smallest prime number that goes into 16? 2, how many times? 8 times. And what goes into 8? 2, 4 times, right? And what goes into 4? 2 times. Okay? So then I have my factors, 2, 2, 2, and 2. So I'm going to rewrite this as the 4th root of 2 times 2 times 2 times 2. So it doesn't matter which method I'm using. I'm going to start out with the prime factorization. I'm going to use the birthday cake method. And I'm going to rewrite my radicand as a prime factorization. So far, so good? Okay. This is what I'm going to do. I'm going to ask myself, what is my index? So in this problem, what's the index? No, what's the index? 4, the number out front, right? That's a 4. So what I'm looking for are sets of 4. So I've got 1, 2, 3, 4 2s, right? So the 4th root of 16 is 2.
Yeah.
Yes, ma'am.
Is this going to be on the return?
A little bit. I think. That's a good question. I will look that up for you. All right. So example 2. So we're going to rewrite 12 a to the 2/3 in radical form. So first I'm going to notice that 2/3 is only with the a, right? So 12 is going to go out front by itself. And I'm going to have my radical. So what's the index of this radical? 3, because if I look at my exponent, it's a fraction, 2 over 3, so my, so my index, thank you, is 3. I was having trouble finding my pen. And then my radicand is going to be a squared. B, same thing. Only notice this time I have parentheses, so everything in the parentheses is going to be part of my radicand. So I'm going to start out with my radical symbol. And what's the index going to be? 5. So then I've got 64a to the 4th. This could simplify, but I'm going to leave that. I didn't ask to simplify for this one, so let's just leave that as 64a to the 4th. Make sure that 4th is inside of your radical. Question?
How would it be wrong if it was outside?
Ooh, if it were outside, we're not going to do that. But if it were outside, it would be the 5th root of 64a times the 5th root of 64a times the 5th root of 64a. So it would be that root 4 times. So it's a similar rule, but it's not a rule we're going to worry about today. Good question. All right, example 3. Are y'all ready? I don't see any pencils still moving. So last example, same thing, only we're going to work backwards. This time, oh no. This time I've given you a radical, and we're going to write this in exponential form. You ready? So I'm going to look first at my radicand. Go for it. You got it. So we've got b to the 3 over, and then my index is 5. That's it. That is it. You've got it, Robin. All right, what about b? All right, so we've got 27 d to the 5th. This is where it gets kind of tricky. The 1/3, right? So do y'all remember our exponent rules that we did just before the break? Sort of. It's been a while. So remember, if we have an exponent on the outside, everything inside is going to get that exponent, right? All right, so I'm going to have 27 to the 1/3 power. And then d, what's 5 times 1/3? 5 over 3.
Oh, I said 5 over 50.
Oh, no, 5 over 3. You're only going to multiply it to the numerator. All right. So I wonder, does 27 to the 1/3, does that reduce?
No.
Let's find out. So I'm going to do the birthday cake method. So 27, what goes into 27? 3. How many times?
7. No. 9 times.
9 times. And what goes into 9?
3.
3 times, right? So 27, I can rewrite 27 as 3 cubed raised to the 1/3, right? And then this is d to the 5/3. Well, what's 3 times 1/3? 3 over 3. So this is going to be 3 to the 3 over 3 power. D to the 5 over 3 power. So that's just 3 d to the 5 over 3 power. That's it.